strata for extended affine Weyl groups.
Yes. So I didn't expect that much to be defined already in my field, but that's lovely. So yeah, it'll be a little bit of repetition probably, but ultimately the goal is the same, to give you some understanding of these words, of this sentence, and to talk about some ongoing work that I have going with Andrea Brini, also in Sheffield. So firstly, we are talking about orbit spaces, which here curly W will always be some sort of Weyl group. And we want to take the complexification of the representation space as such and the closure. And already we've heard about Chevalier's theorem that states that we have the coordinate ring being a complex ring of these invariants or basic invariants, yi. So here, x are the coordinates on V, the vector space, and this L is the rank of the associated algebra or number of Lincoln nodes or so on. Right, so the second thing I want to define is the discriminant in this world, and that is the union of irregular orbits of the Weyl group, or equivalently, the image of the union of mirrors, so union of hyperplanes in the root space under the image down to the orbit space. And this discriminant has stratification given by the codimension. Right, so a little more Frobenius stuff. The cytometric is what I want to define here. So again, well, as usual in our field, metric is really a little bit like metric. It's synonymous with a metric non-degenerate bilinear form, not necessarily positive semi-definite. And a Frobenius manifold, we have heard the definition, which is lovely because I was not planning to give it. But the important part here is that the orbit space does have a Frobenius manifold structure away from the discriminant, and it is equipped with this pencil of flat metric. So we've seen that G metric, which is induced by the killing form, and that this is the intersection form, which has been mentioned by a couple of people. And this eta, which is that's the cytometric or the cyto form, which I will be focusing on, and it's defined as a dual of this, that L is nothing to do with Lagrange transformations. It's the lead derivative in direction of this unit vector field, E, lowercase e. So the kind of point of this talk, in some sense, is to investigate the determinant of the cytometric on the discriminant. But there's an obvious problem here, that one of the reasons that we define a Frobenius manifold away from the discriminant is exactly because eta is degenerate on it. So what do I mean when I am talking about eta on the discriminant? And that is as such, that I'm talking about the pullback of the embedding of any discriminant stratum into the orbit space. And then you can sort of ask some basic questions, like, okay, so we now have a non-degenerate metric. Is it still flat? And the final one, what form does it have? So can we find some kind of nice factorization? And that third question is inspired by the fact that upstairs in the Frobenius manifold, you have a factorization of the determinant beta in terms of these defining polynomials of hyperplane arrangements. So for Weyl groups, the answers are all existing. So yeah, it is non-zero, which is lovely, and it is zero when you naively restrict onto the discriminant of the discriminant stratum, so to speak. So on further discriminant strata of higher codimension, which is what we would expect. It's not flat, and this is a very general fact, and is expected by some already existing stuff in literature. And the determinant does factorize very nicely in terms of linear forms. And this is a result by Antonio Feigenand Stram from 2020. I hope that year is correct. But yeah, I don't really want to go into what this KH, the multiplicity, is, other than it is a Coxeter number of a certainly reducible Weyl group, because otherwise I would have to define a bunch of things. But I mean, of course, if you're interested, you could ask me after or whatever. So we'll come back to it in an example a little bit at the end. Right, so that whole story is lovely for the Weyl group. But obviously my title has to do with extended affine Weyl groups, so I better talk about them. So firstly, the affine Weyl group, I will always denote that. And I mean, it's the same story as the non-affine, only now the invariant, basic invariants are now Fourier polynomials. So exponentiated polynomials in the linear coordinates on V. And here, yeah, the omegas will always be fundamental weights. Then we define the extended affine Weyl group with another copy of semi-direct product with a copy of Z. And the action is generated, well, this first guy is really just the affine action. And then you have the addition of just shifting your final affine coordinate, xl plus 1, where L was the rank of the associated algebra. And here comes an omega k, and this k is exactly the label of the marked node that Ian was talking about. And this is a unique choice for all the drinking types, except for A, where you can pick any one. And for this talk, I will stick to having this choice throughout. Right. So in 1998, Dubrovin and Chang, when they defined this construction, they showed that, yes, you do have a Chevalier type theorem for the extended affine orbit spaces as well. And it is a Frobenius manifold, away again from the discriminant, and the intersection form is given by just an orthogonal extension of the Pelling form. There should really be some kind of 4 pi there, but that's not important for now. And again, you obtain eta as derivatives of this intersection form. Right, so before I go further, I wanted to make a small digression, which, again, yeah, this has been more talked about than I expected so far. And that has to do with this Lambda-Ginsburg superpotential or Lambda-Ginsburg model in the world of Frobenius manifolds. So what that is that you have a family of functions, meromorphic functions in my world, and you can construct the Frobenius manifolds on the parameter space of this family. And by doing that, we've already seen this formula where you can find the entries of your eta, well, gram matrix of the eta metric, as taking residues summing over critical points of lambda, of this Lambda-Ginsburg superpotential. And as we had some discussion on, the primitive form here is the logarithm. So it's P is really the log mu or whatever favorite letter you want to pick as coordinate. Right, so in our paper last year, we found Lambda-Ginsburg models for all the extended affine Frobenius manifold, so the Dubrovin-Chang Frobenius manifold in a uniform way. So the classical cases were already done, but they were done in a different way that couldn't be, they couldn't do the exceptionals in that way. So we did this by considering a characteristic equation, so a spectral curve coming as a characteristic equation of some integrable system. And in this way, you get a curve that is potentially higher genus for all the exceptionals except for G2. You will have a non-zero genus curve. And it's really, really quite complicated in the E cases, especially E7, E8. But nonetheless, they're very explicit, and we obtain explicit prepotentials. And that is crucial for what I want to talk about now, because in the, wait, did I haven't cancelled that slide, did I? Oh my God, that's, oh no, yeah. So here, in the theorem for the non-affine Weyl groups, for the classical cases, they also, well, you and they also use the superpotential very actively, in which case the superpotential is rational and you can manipulate it in various ways to find an explicit expression for the determinant in some nice coordinates. So that we can do in a, and we did, in a very similar fashion. And what we got was that this expression here. So in our, this E det AFS, that just means that it's kind of the exponentiated result of the previous result. So what I mean by that, like, if they had some kind of factor x1 minus x2 squared, then that guy would look like e to the x1 minus x2 squared minus 1. So it's really quite natural, in so to speak. And then you have an exponentiated guy, which is directly just related to this extension that we did for the extended affine Weyl group. The L+1 was just the extra affine coordinate, and they're very, like that just sits outside the whole time. And this in the bottom comes from the fact that our superpotentials are no longer, well, they're rational, not just, they have poles in this P or this mu rather. And that factor carries on the whole, carries through the whole calculation and has exactly the same positions and the poles and the orders of the poles of the superpotential. This will be more clear when I show a little example. But this seems true this is true for all the classical cases. And then the question becomes, okay, maybe this holds for exceptionals, which would be lovely, but that's interesting. Right, so exceptionals. In the, again, in the non-affine case, the authors also had to use a different method, because I don't think they had access to superpotentials in that case. We do, but we still can't use it, because you can't solve for lambda in a nice way. Lambda is multi-valued, it's complicated, and even working implicitly, it gets very, very, very ugly and complicated. And even in G2, where the genus is 0, and you could technically solve for lambda for the superpotential to get a rational function, it's some of the tools that we use still don't follow naturally. So we needed to come up with a different way to do it, which sadly is not the way that was done in the non-affine case, because we have these exponentiated coordinates, which makes the computation on a computer really, really complicated, and the computer doesn't want to do it. But we have a way out, And the way out is to think of the discriminant strata as exactly how they are mirrors to simple roots. And in that sense, you can characterize them by simply thinking of parabolic subgroups. So pretty much just removing the number of thinking nodes according to the codimension of the strata that you want. And why this is smart is that in our spectral curves, they come very naturally with a set of coordinates, which are characters, fundamental characters of the affine Lie group. And in that way, you can simply use Mathematica or SageMath or your favorite software to do branch rules, as the physicist calls it. So writing characters upstairs, remove a thinking node, and then project down to write these characters in terms of fundamental characters on the sub algebra or sub group. And so far that's working very, very well. And the example that I wanted to show is a simple guy, but an exceptional guy. So this is G2 going to A1 in removing the first node, so removing the node that arrows point away from in the Denkin diagram. So you have like alpha 1, alpha 2, and 3. Yeah. So what we're doing is we're basically removing that, or in other words, setting alpha 1 equal to 0. Here are little w's, lowercase w's are the fundamental characters of the G2 situation. And then you can do branch rules to go down to write them in terms of fundamental characters of in A1. So those are the capitalized W's. And if we do that, we simply get a superpotential that we say is the superpotential restricted to the discriminant stratum. Right, now we can use that residue formula in W coordinates. It's quite a nice one. You can turn the contour around and etc. and make it quite reasonable and get a result in terms of W. Right, and the Jacobian is pretty simple because the Jacobian doesn't see any of this extended stuff because the W0 part just follows through again. Okay, and then you can translate to X and see that you get a nice factorization in now exponentiated linear forms. But so the final step is then to make sense of these multiplicities. Right. So you can be a little clever. So, well, it's not that much fun. If you just say that, fine, you set your coordinate to be e to the x1. Remember, this is a two-dimensional stratum. So d equals to 1. Then you can rewrite your determinant to be proportional to that guy there. And then you compare with the superpotential, and you can see that the denominator is exactly the same if you just map mu to psi. And the numerator has the multiplicities that exactly is expected from the recipe given by Antonio Strauss and Fagan. So these are the things that I didn't really want to talk about, but the lovely thing is that it's exactly the same multiplicities exponentiated as their case. So really, we don't have to do this work in the classical cases. And then exponential cases, you can do it anyway.
Ask a question. So you're saying in G2, you actually see B2 as part of the story? This is the G2 example?
To go, yeah, exactly. So, yeah, okay. So maybe this has to do with, so beta here is a multiple of this linear form in the factorization. So it would be x1 minus x2 when you restrict. So they are the same in the restriction. So it can be anything really upstairs as long as it restricts there and it's independent of that choice. Up to that freedom.
Can I ask one more question? So it's not, you're not taking the extent, because if you remove a node from the extended Dinkin diagram, then you would get an A1 cross A1.
Oh, yeah. No,
and an A2, but you get, this is different.
This is non-affine.
This is non-affine.
Yeah.
Okay.
So we're kind of reducing the problem from dealing with the extended affine to a problem just relying on results and methods that are in the non-affine case, which is a lot easier to deal with. Yeah, so this is just the root system generated by this beta guy and associated to the discriminant strata. And then this is an irreducible component in which beta lives in.
So does B2 arise indeed? How do we get B2 inside? Is it inside G2?
It's, oh yeah, whatever. So RD beta equals RD, comma beta, and beta is necessarily not in RD because it has to do with the this guy. So this can be, this has an orthogonal decomposition into irreducible parts, and one connected component, which is notated R0, is the one that contain beta. And it turns out that that is of type B2. We can see that by looking at the size, really. And so then the multiplicity that you expect is the constant number of that. And I see now that they are the wrong way around, but the 2 should be on the x1 and the 2x1 is for the 4. Does that make sense in the multiplicities? So this kind of a baby exceptional example. The other node, you can do the same, and it's a little more complicated. And then we are currently calculating all the discriminant strata quite explicitly for F4, E6, E7, E8. F4 and E6 is done. I'm trying then to make sense of this in a factorization way. And I mean, you could ask the question, why am I bothering with this? Partly other than it's a nice generalization of some previous work. But also these discriminant strata are, while not Frobenius manifolds, you still have a lot of structure on them. You have almost duality there, which Ian talked about. You have integrable systems associated to it. And then having these superpotentials restricted to discriminant can then help us talk about and describe these structures. And that's really all I want to say.
Well, questions, yeah, sometime I